Captions in English, please. So this is the second video of chapter 12. We will focus on ionic bonding and pure covalent bonding. So what is the ionic bonding versus molecular or also covalent bonding? So note how molecular is synonymous to covalent. So you can use one or the other and it means the same thing. So the basic units that compose dry ice, for example, the carbon dioxide when it's solid, are molecules, CO2 molecules. So dry ice is a molecular compound. It's made of CO2 molecules and they are packed together in an ordered fashion when it's in the solid state. But the basic units that compose table salt, which is an ionic compound, are NaCl formula units. We call them formula units. So when you have an ionic compound, you call the basic unit formula units, and when you have a molecular compound, you call the basic units molecules. So let's look at ionic compounds first. So we know metals have the tendency to lose electrons, and so when a metal combines with a non-metal, and non-metals have the tendency to gain electrons, so one or more electrons can transfer from the metal to the non-metal, creating positive and negative ions that are attracted to each other, right? We know that opposite charges are attracted, and so when you have a positive ion and a negative ion, they will be attracted. And that's how you can make ionic compound. And that's what typically happens between nonmetals and metals. So a compound composed of a metal and a non-metal is considered ionic. So by definition, an ionic compound is made of metal and non-metals. And so the basic unit for ionic compound is the formula unit. So don't talk about molecules when you are talking about an ionic compound. Unlike molecular compounds, ionic compounds do not contain individual molecules, but rather cations and anions in an alternating three-dimensional array. So because positive ions are attracted to negative ions, the cations will be surrounded by anions, and then the anions will be surrounded by cations. And so this creates an alternating 3D lattice or array. So how are ionic compounds made? So for example, why is the formula for potassium bromide KBr? So we know potassium is an alkali metal from group 1A. It likes to lose one electron to become a positive cation with a one positive charge. So this is shown as K becomes K plus one electron. The electron is gone from the atom K, and you have a positive ion, K plus. Bromine likes to gain an electron and become the Br minus electrons. And so chemically we can write this as Br plus one electrons becomes the Br minus, the bromide ion. So we can explain why these ions form based on their electron configuration. So why do they do that? It's because KBr, for example, has this electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And so the valence shell for potassium is the fourth, and there is only one orbital with one electron in there, the 4s1. And so it's easy for potassium to give away that one 4s electron. And so by doing this, potassium, which started with 19 electrons, will have then only 18 electrons. And 18 electrons is the configuration, the electron configuration for the noble gas argon. So when you're removing that 4s1, the electron configuration for K plus is 1s2, 2s2, 2p6, 3s2, 3p6, which is exactly the electron configuration of argon. So you can write that it's argon in brackets, which means it's electron configuration. And we know that the noble gases are very stable. They have a very stable electron configuration because all their orbitals are full and their valence shell is, the 3s and 3p is full, so it makes argon very stable. Bromine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. So the valence shell for bromine is also the fourth, and there is 2 electrons in the 4s orbital and 5 electrons in the 4p orbitals. So bromine is closer to krypton. You can see that by gaining 1 more electron in its 4p orbitals and becoming the 4p6, it has the same electron configuration at krypton, because bromine has 35 electrons, but by gaining 1 more electron, it gets 36 electrons, and that's the number of electrons of krypton. So Br minus has the same electron configuration as krypton, and that makes it much more stable. So when these elements form ions, they achieve a noble gas configuration, and noble gas configurations are very stable, and so all elements try to reach that these stable noble gas configurations. Let's look at another example. What is the formula for aluminum oxide, Al2O3? So aluminum is in group 3A, likes to lose 2 electrons and becomes a 3 plus ion. So aluminum becomes Al3 plus and 3 electrons are gone from aluminum. We know that oxygen likes to gain 2 electrons to become a O negative 2 anion. So again, we can explain why they do this by looking at the electron configuration of aluminum first. So aluminum has electron configuration of 1s2, 2s2, 2p6, 3s2, 3p1. So the valence shell of aluminum is the third. It has 3 electrons in it, the 2 electrons in the 3s orbital and the 1 electron in the 3p. So, sorry. And so aluminum likes to lose those 3 electrons in its valence shell. And when it loses that 3p1 and 3s2 electrons, it gains the same electron configuration as neon, because aluminum had 13. Atomic number 13 means it has 13 electrons, but by losing 3, it gets 10 electrons only. And that's the atomic number of neon. So then aluminum 3 plus has the same electron configuration as neon. Let's look at oxygen. Electron configuration of oxygen is 1s2, 2s2, 2p4. By gaining 2 electrons, filling that 2p orbitals with 2 more electrons, it becomes 1s2, 2s2, 2p6. And that's 10 electrons in total. So it's again the same electron configuration as neon. So that's why aluminum and oxygen do like to gain 2 electrons for oxygen and lose 3 electrons for aluminum, because they become electronically like neon, which is a stable configuration. So each aluminum wants to lose 3 electrons, and each oxygen can only accept 2 electrons. Therefore, the formula must be Al2O3. They must exchange 6 electrons in total. So 6 electrons will be transferred in the process. And remember how we can also find this formula of Al2O3 by doing the crisscross trick, where you take the charge of the anion, oxygen, the 2 becomes the subscript for aluminum, and the 3 from the charge of the aluminum becomes the subscript for oxygen. But by calculating the number of electrons exchanged, you see it's 6 electrons. So that's why aluminum oxide has this formula Al2O3. So how strong are ionic bonds? Ionic bonds are extremely stable and their bonds are very strong. Let's look at the boiling point and melting point of sodium chloride to see how strong this is. So the melting point for salt is 801 degrees Celsius, and the boiling point is 1413 degrees Celsius, which are very high temperatures. So that means you need to bring a lot of energy to break the bonds between chlorine and sodium, which justifies the fact that this bond is very strong. By comparison, if you look at water and its melting point and boiling point, it's 0 degrees Celsius for the melting point and 100 degrees Celsius for the boiling point of water. So you see that it doesn't require as much energy. You can do this at home, while melting sodium chloride, you cannot do that at home. You need an industrial furnace. So this shows you how strong the bonds are in ionic compounds. So now let's look at covalent bonds. And let's look at the simplest type of covalent bond, which happens between two identical atoms of hydrogens. Hydrogen is a diatomic molecule, and it's in its natural state, which is a gas. It is described as H2. So you do not find hydrogen atoms by themselves in nature. What you find is a diatomic molecule made of two hydrogen atoms bonded together. So how can we explain the bonding in H2? Why do they do that? Well, you've seen in the video in the previous recording how this is due to the fact that their respective energy gets smaller when they get together. So when two hydrogens get close to each other, the electron of one atom is attracted to the nucleus of the other and vice versa. So you know how electrons are negatively charged and protons in the nucleus of an hydrogen atoms are positively charged, and so they are attracted. And so the electron of one atom is attracted to the nucleus of the other. And so the greatest electron density is between the two atoms. And so that makes the two atoms shared between by the two nucleus. They are shared equally because it's two atoms of the same kind. So we would call this a pure covalent molecule. So what drives the two hydrogens to form a bond in the first place? The simple answer is energy, and I just said that earlier and too soon actually. But yes, it's because it lowers the energy of the two atoms by being together. It lowers their energy and that makes them more stable. Because in chemistry, you have to realize that whenever you have a low energy, it means you are more stable. And so H2 is more stable than the separated atoms. And you've seen that in the video earlier, in the previous recording. But let's look at this electron microscope imaging of two rhenium atoms. So it's a molecule made of two rhenium atoms, and we see them as two dark spots here in the upper part of the image. They travel around two carbon nanotubes, and that's the lattice. So you see kind of two tubes made of contrast, dark and light contrast. And so those two radium atoms will be moving and settling into the gap between the nanotubes. And when the atoms are separated by a larger distance, the bond between them is broken, but then it reforms. So you will see how they are more stable when they are close together. So focus on the right side of the image, and where right now it looks like one dark dot, but there will be two there. Don't look at the groups of 10 or 12 dots. Focus on the single black dot here in the top of the second nanotube. So if you look here, you see those two atoms. Sometimes one is hidden because it's behind the other, but they are bonded here and they move. And now they are between the two carbon nanotubes, and they keep moving because atoms are not still; they always vibrate. And here they keep moving and they stay together. Let's see if they get separated again. Oops, they got separated, but they feel like attracted to each other, right? And the reason is because it lowers their level of energy when they're staying together.